I'm going to assume that you're able to read these or to watch these videos, or else I'm going to make them again. But here we go. Let's look at some examples. So what is the pH of? Again, I'm going to kind of make these up and do the calculations as we go along. So let's say, for example, I say, what is the pH of, oops, 0.13 molarity hydrofluoric acid. All right. What is the molarity of 0.13 molarity hydrofluoric acid? Step number one, identify is that an acid, base, or salt. It should be pretty obvious to you that's an acid because the name of it is hydrofluoric acid. Once we've identified, is it an acid? The next thing we say is it strong or weak? This is one that a lot of students think, well, it's strong. Hydrofluoric acid is strong. It's not. It is not on your list. Double check your list. It is not strong. It is weak. So it is an acid and it is weak. And therefore, I am going to begin this problem by writing an equilibrium reaction. And I'm going to have to scroll up so that I've got space to work. So I'll post this, an image of this so that you can have it up on your screen if you want to as you're going back through this. I'll take care of that later, which may be earlier once you're watching this. So I can actually look up the formula for hydrofluoric acid if I don't know it. Don't guess. Look it up. If you don't know it, look it up. And where can I look it up? I can Google it. Or I know from my flow chart, I'm going to need a Ka value, so it should be on my tables of Ka values. So look it up. This is a good time to point out that our tables of Ka values and Kb values in the textbook are the tables that you should be using. If you Google what's the Ka of HF, hydrofluoric acid, you may get a number that's slightly different than the table that we're using in our textbook. These tables are experimental data. They have to be measured in the laboratory, and it is notorious for typos to happen. And so if you look at 2 or 3 different tables for Ka values, you may see 2 or 3 different values. They should all be similar. They should all be close to each other, but they might be slightly different. That's going to give you the wrong answer for our homework, quiz, and exam problems. You should be using our tables, the ones linked in your course content. And when I look up hydrofluoric acid, I do see that the formula for hydrofluoric acid is HF. And so I'm going to write that equilibrium reaction with HF, which can be simply that. There's that equilibrium reaction. I'm going to need a Ka value, so I'm going to go ahead and look up the Ka value for hydrofluoric acid. It is 6.4 times 10 to the minus 4. And I'm going to need an ice table, and I'll need the ice table for the HF. And I'm going to have an initial, a change, and an equilibrium amount. And you're going to notice exactly the same pattern for almost all these problems. You're going to get into a rhythm here. The initial amount of hydrofluoric acid is 0.13 molarity. And so that's the number that goes right there in that initial amount. At the beginning, when I make the solution, I am making it 0.13 moles of HF molecule per liter of solution, and therefore the 0.13 goes there. And before it comes to equilibrium, these will be 0. And then as it reaches equilibrium, it will be minus X, and plus X. All of our weak acids and bases have a 1-to-1 stoichiometry. Back in module, shoot, I should have this handy. Back in module 5, when we first learned equilibrium reactions, sometimes the stoichiometry wasn't always 1-to-1. You have to watch that. When we get to module 8, the stoichiometry is not necessarily going to be 1-to-1. You have to watch that. But with weak acids, weak bases, it's all 1-to-1. So that's wonderful. I'm going to finish up this ice table. Again, you should be getting good at this. And then I'm going to plug this into the Ka expression because it's what is the pH of. To get the pH, I need the equilibrium concentration of H+, so I can calculate the pH. I need to solve for X, just like we were doing in module 5. So Ka is equal to the H+ times the F-, all over the concentration of HF. It is also equal to 6.4 times 10 to the minus 4. That's the numerical value I looked up for the Ka. So that's equal to x squared all over 0.13 minus x. Now, there is an approximation that we can almost always use so that we don't have to do the quadratic equation, and that's looking at this denominator, 0.13 minus x. Your textbook talks about this in one of their sample problems, but let's go over it now. 0.13 minus x is going to be very close to 0.13 if x is very, very small. For example, if I have $1 million and I give everyone in this class this semester, if I give everyone $1 out of my pile of $1 million, how much money do I have left? Okay, I've still got $1 million left because the amount I'm giving away is very small compared to the amount I originally had. So as long as x is very, very small in this equation, it's essentially equal to the original amount. And this is a pretty good approximation that you can use for these. Now, if this approximation doesn't work, you have to use the quadratic equation, and I encourage you to use a quadratic equation solver online. If this is a multiple choice question and the answers aren't really close to each other, you still should be able to pick it out, even if the approximation doesn't work exactly. It works almost perfectly every time, and it works perfectly most of the time. So let's use that approximation, and let's rewrite our equation as 6.4 times 10 to the minus 4 equals x squared divided by 0.13. We changed the 0.13 minus x. We made that equal to be just 0.13. So there is our equation. It is very easy at this point to solve for x. You essentially, I'll only go over this algebra once. I'll skip to the chase the rest of the time. But essentially, you say, well, that's 0.13 times 6.4 times 10 to the minus 4. That's equal to x squared. Then to get x, I take the square root of the 0.13. I can actually get a numerical value here, but I don't want to round. I don't want to round in the middle of these calculations. So when I'm punching it into my calculator, I want to keep all the digits. So I'm going to punch in 0.13 times 6.4 exp negative 4. I'm going to take the square root, and my x is 9.12 times 10 to the minus 3. This is a good time to check that approximation that x was very, very small. And in order to do that check, all right, you take 0.13 minus x, or 0.13 minus your 9.12 times 10 to the minus 3. I'm going to store that in my calculator so I don't have to plug it in again. And what I get is I actually get 0.12. So this is not a great approximation. It's not great. It's going to be very close, but it's not great. Let's go ahead and go with it, and then we'll fix it in a minute. It's not a great approximation, but it should be very, very close. So let's go with it. And therefore, my hydrogen ion concentration, which is my X, just to remind you, in my ice table, X is my hydrogen ion concentration. So X is equal to 9.12 times 10 to the minus 3, except for I'm not rounding that yet. I have that number stored in my calculator. And so pH is equal to the negative log of that H plus. Again, I am not punching that 9.12 times 10 to the minus 3 in my calculator again. I'm just pulling it up on my calculator and taking the negative log, and I get 2.04. I get my pH as 2.04. If I solved for this exactly using the quadratic equation, I will get something very, very close for it. All right, if I use the quadratic equation, it might be, actually, sometimes it's exactly the same, but if I use the quadratic equation, it should be very, very close. And again, on a multiple choice question, this would be close enough that you should be able to pick it as long as there weren't two answers very, very close to each other. When you have to type in your answer, okay, this might not be close enough. Use that quadratic equation solver. Google how to use the quadratic equation solver, punch that in. All right, So it should be very, very close. If if you'll bear with me just a minute, if I use the quadratic equation exactly, I will get, I'm going to do it on my calculator real quick. All right, if I use the quadratic equation on my calculator, I get x is equal to 8.806 times 10 to the minus 3. So very, very close to my original x. All right. My original x was 9.12 times 10 to the minus 3. If I use the quadratic equation, I'm going to get that, which again is going to be equal to the h plus, which means that using the quadratic equation, I get the pH is 2.06. You see how that's different in the third digit? That may be far enough off that on a type in this answer, you're going to lose some, it'll count it wrong. If I come back in and do partial credit on a quiz or an exam, you'd get partial credit back. But it's important to do that quadratic if your assumption doesn't work. I always try the assumption first because it's so quick. And if I end up with that check, if I go back and check that and it doesn't quite work out, I should be getting 0.13 when I do this check, and instead I got 0.12. So if I come back and I do the check and it's not quite right, then I do the quadratic equation. So the answer to the question is, what is the pH of that solution? It's 2.06. Oh, one last thing. It's a good idea at the end of each of these problems is to go back and say, I was looking for the pH of hydrofluoric acid. Hydrofluoric acid is a weak acid. I'm expecting a pH in the acidic range. That's again a module, was that module 6 kind of concept. Is 2.06 in the acidic range? Yes, it is. So that makes sense. That's a good way to catch silly mistakes. And so the pH here is 2.06.